All right, let's jump right in. We're about to tackle one of the most powerful, most foundational ideas in all of AI, and honestly, one of the most misunderstood. It's this concept you hear thrown around all the time when it seems to promise almost limitless potential for artificial intelligence. Yep, I'm talking about the universal approximation theorem.
You've definitely seen something like this online, right? On a forum, in a blog post, somewhere. It's this huge, kind of seductive claim. It makes it sound like because neural nets are universal, they can learn to do, well, literally anything. And that AGI, artificial general intelligence, is really just one huge smart network away. But is it really that simple?
So here's our game plan. We're going to start with that big universal promise. Then we'll break down the simple but super powerful idea at its heart. After that, though, comes the reality check, the massive gap between the theory and how things actually work in practice. We'll get into why going deep often matters more than going wide, and finally, we'll put this whole idea to the ultimate real-world test.
Okay, part one, the universal promise. The core idea here is, well, it's almost magical. It suggests that even a really, really simple neural network has, in theory, the power to learn and map out pretty much any relationship you could find in a set of data. Anything. So how on earth is that even possible? How can such a simple structure be so incredibly powerful? Well, the intuition behind it all is actually beautiful in its simplicity. It really just comes down to building blocks. I love how this slide visualizes the whole concept. Just imagine you have some crazy, complex, winding curve. What the theorem says is you can get super close to drawing that curve just by piecing together a bunch of tiny little flat steps. It's like building with Legos. Each individual neuron in the network can be taught to create one of those simple little steps. And if you combine enough of them, you can build a shape that gets unbelievably close to that original complicated curve.
And that brings us to the formal statement of the theorem. Get this. A neural network with just one single hidden layer can get as close as you want to any continuous function. Basically any function that doesn't have wild, sudden jumps. But there's a catch, a big one. It's that last little phrase, provided the layer has enough neurons. And that phrase, enough neurons, well, that's where things start to get really complicated. Which brings us right to the great divide, the huge gap between theory and practice. The mathematical promise is absolutely incredible, but it comes with some major real-world warnings. You gotta read the fine print. And this is the million-dollar question, isn't it? If the math guarantees this amazing power, why aren't we done yet? Why haven't we solved every single problem? Why isn't AGI already here? Well, the answer is hiding in that fine print. So let's blow up that fine print. First off, the theorem says a network can approximate a function, not get it exactly right. There's always going to be some error. Second, and this is a big one, the UAT is what's called an existence proof. It guarantees that a network that solves the problem exists somewhere out there, but it gives you zero instructions on how to find it, how to build it, or how to train it. Third, that little phrase, enough neurons, in the real world, that could mean a number so ridiculously, astronomically large that you couldn't build it with all the computers on Earth. And finally, the theorem says nothing about the most important part of AI in the real world, learning from a limited amount of data and then being able to generalize to new stuff it's never seen before. And here's a perfect picture of that gap. When a network tries to model data that isn't perfectly smooth, it can create these bizarre artificial connections between different points. These are sometimes called spandrels. The model is basically just guessing, filling in the blanks, because it assumes everything is connected smoothly. It really shows you the massive difference between a perfect math problem and a real-world trained model. This all leads to another massive question. The theorem is all about a single, super wide layer of neurons. But is that actually the best way to build a network in the real world? Let's just compare the two. A shallow, wide network does a ton of simple calculations all at once in parallel. But a deep and narrow network, it builds up ideas layer by layer in a more structured, sequential way. And for tons of real-world problems where simple ideas build into more complex ones, like pixels forming edges, edges forming shapes, and shapes forming objects, that deep, layered approach is just way, way more efficient. So here's the real kicker. Research has shown that deeper networks can be exponentially more powerful and expressive than shallow ones, even if they have the exact same number of neurons. Adding layers gives you so much more bang for your buck than just making one layer wider and wider and wider.
But even beyond the pure math of how to build a network, there is an even bigger, more powerful force that decides what AI can and can't do. And that force? It's money. This quote from an AI engineer just cuts right to the heart of it all. Yeah, the theoretical possibilities are fascinating to talk about, but what actually gets built is decided by the cold, hard logic of market economics. And this chart just lays it all out, doesn't it? Building and training huge AI models is incredibly expensive. We're talking six-figure starting salaries, years and years of development time. This massive cost forces companies to focus on solving problems that are practical, efficient, and pretty much guaranteed to make a profit. So the ultimate limit isn't some beautiful mathematical theorem, that impossibly large network that can theoretically do anything. It's a non-starter in the real world. The market is always going to select for solutions that are efficient and useful right now, not some theoretical unicorn that might exist in the abstract. Which brings us to our final takeaway. The universal approximation theorem is absolutely vital. It's the mathematical guarantee that we're on the right track, that neural networks are an incredibly powerful tool. But it is not a roadmap to AGI. Think of it as the foundation of a building, not the completed skyscraper. So in the end, the theorem proves what's possible in the world of pure math. But it leaves us with a much harder and, frankly, a much more human question of all the infinite things we could teach an AI to do. What problems out here in the real world are actually worth our time, our money, and our effort to solve?